be able to.
All right, we're going to go over compositions of functions today, and we're going to start with a real world example so that you can see how that ties into the math part of it. It says Betty's in the market for a new flat screen TV. She has two coupons that she can use to purchase the television. One coupon is 20% off the original price, and the other coupon is $100 off the original price. So we're going to start by writing a function for each one of these coupons. It says write a function p of x to represent the discounted price of the television after the 20% off coupon is applied. So for this one, we're going to call that p of x. So we've got p of x is equal to, and it's going to be the price of the television minus 20% of the television price. And so remember, when we put a percentage into an equation, we move that decimal over two places. So for the 20%, we move it over to do 0.2. So 0.2 times x is going to give me 20% of the television price, and then x minus that is going to give me the price after that coupon is removed. For part B, it says write a function d of x to represent the discounted price of the television after the $100 coupon is applied. And so in this case, d of x is equal to the price of the TV minus $100. All right, so it says, which coupon should Betty use and justify your answer? Well, that really is going to depend on the price of the TV. So if the 20% is less than $100, well, then she should use this one. But if the 20% is more than the $100, then she should use this coupon. So if we were buying a TV for $500, then the 20% off is 100, and so both of those would be equal to each other at that point. So anything above the 500, this is a better price. Anything under the 500, this would be a better coupon to use. All right, suppose Betty is able to use both coupons if the television that she wants costs $350. In which order should Betty apply the coupons to yield the lowest final price? Show your work. Well, in this case, her TV is $350. So we're going to want the 20% off coupon first because that's going to make it the highest it can be. And then the $100, it doesn't change, so we would subtract the $100. But we'll look at both of those examples so you can see how that works. So if we had $350 minus 0.2 times $350, that's going to give us $280. So we took the price of the TV of $350 and we subtract 20% of $350 and we got $280. And then we would subtract the $100 and we get $180 in this example. So for our other one, we start with the $350 and we subtract the $100 coupon, and that gives us $250. Now we're going to subtract the 20% off coupon. So we do 250 minus 0.2 of 250. And that's going to give me a price of $200. So this one was the better deal. First, I take the 20% off, and then I take the $100. All right. So we're going to put that thought into one function. It says, suppose Betty uses the 20% off coupon first, followed by the $100 off coupon. Write the function t of x that represents the discounted price. So now we're going to call this one t of x, and we're representing what we did up here. And so we took the full price of x, and we subtract the 20% off coupon, and then we subtracted $100. And so if you put that together, that would be 0.8x minus 100. So that is our t of x function. Now we're going to do the other one. And we're going to call this one m of x. And so in m of x, we took the full price of the TV and we subtract $100. And then we subtracted 0.2 of that price, so x minus 100. And so we're going to distribute here. And then we combine our like terms. And so we've got x minus 0.2, so that's going to give us 0.8x. And then we've got a negative 100 plus 20, which is a negative 80. And so there's our two equations. What we just did there is called a composition of function. It tells us the process of evaluating one function inside of another function is called compositions of functions. For two functions, f and g, the composition of functions uses the output of g of x as the input of f of x. It is notated in these two ways. I personally like this one better here, but we are going to show you both. This is the one that shows up on the SAT and ACT quite a bit. So you do want to understand that that little circle right there stands for compositions. This is still the G inside of F. Now, to me, this one demonstrates that better. You can see the G of X inside of the F. So this means X is the input to G, and all of that is the input for F. So the resulting function is called a composite function. The two functions, t of x and m of x, you wrote in questions 3 and 4, can also be written as compositions of the original functions p of x and d of x. So we're going to rewrite t of x as dp of x. So d of p of x is our 0.8x minus 100. And then p of d of x is equal to our 0.8x minus 80. Those can be written as compositions because that's what we did here. We plugged one into the other equation. All right, we're going to see that now in math terms here. It is given that f of, whoops, here we go. Given that f of x equals x squared plus 1 and g of x is equal to 3x minus 5 and h of x is equal to 2x minus 3, find the following compositions. So this is saying g of x inside of h. So I'm going to start with this on the outside, and I'm going to put g of x inside this equation. So h of x is 2, and then we're in the place of the x is going to be my new function, minus 3. So 2x minus 3, that's what my h of x function is. That's the outside. And we're going to plug in this g of x in the place of the x. So the 3x minus 5 goes right inside there. Now we distribute, and so we get 6x minus 10 minus 3 is equal to 6x minus 13. And so there is my composite function. All right, this has the other notation. Again, I prefer the other one, so sometimes I rewrite it to look like that so you can see the g of x is the one that's going inside the f function. You can write it with either notation. They both mean exactly the same thing. Now, the f function is the one that's going to be on the outside here, and the g of x is going to be on the inside. So my f function, that's this one. Here's my f. This is going to be the outside part, so x squared plus 1. In the place of the x, that's where my g of x goes. This is my new input for this function. So I'm going to replace the x. Notice that I am only replacing the x. No other part of the equation is changed. We just have a new input. So x is the input for g, which that's what it is here. And then all of that is the input for f. So all of this goes in the place of the x in the other one. Now we simplify. So 3x minus 5 squared. I FOIL that. We've done a lot of that this year. So that gives us 9x squared, because 3x times 3x. And then the 3x would be multiplied times the negative 5 to give me negative 15x. And the negative 5 would be multiplied with the 3x, giving me another negative 15x. So that's negative 30x. And negative 5 times negative 5 is a positive 25. Don't forget that plus 1. Students forget that a lot, but we've just FOILed this out. We still need that plus 1 at the end. Now we combine our like terms. And there is our composite function, 9x squared minus 30x plus 26. All right, for our g of f of x, g is going to be on the outside, f of x is going to be on the inside. So I've got 3, my new x, minus 5. That's what the g function is, 3x minus 5. In the place of the x, we're going to put our f of x equation, which is x squared plus 1. We distribute. And so g of f of x is equal to 3x squared minus 2. So that's compositions of functions. It could be used quite a bit. Last time we talked about inverses of functions, and so you can actually prove that two functions are inverses of each other by using compositions. If you do f of g of x and get x, and you do g of f of x, then f of x and g of x are inverses. So if you do the composition on both of them, and you get an x, then they are inverses of each other. So let's look at how that works. Right here, we've got f of x equals the square root of x, and g of x is equal to the square root of 2. So first I start, and you do have to do both of them, not just one. So when it asks you to do this on the test, make sure you do both. All right, so we're going to start with f of g of x. You can start with whichever one. I'm going to plug the g of x in the place of the f of x, and so I get the square root of x squared. Now, when we simplify this, that cancels, and I get x. Now I try g of f of x, and so the g one is the one on the outside, and that is x squared, and I'm going to place that square root of x inside. And so then the square root and the square cancel, and we get x. So we know that these two are inverses because they both came out to be x. All right, it's probably time for you to try one. So you try 9. Go ahead and pause the video, come back and check your work. So check your work. That one was an inverse as well. Since when I did the f of g of x, I got x, and when I did the g of f of x, I got x. Now you do have to show all of the steps, so don't just go from this first one and try and cancel everything at once, because that does not work. You have to follow order of operations. And so the first thing we needed to see was that this plus 2 and minus 2 canceled. I can't cancel the square root and the square if these two are still inside. So I cancel that, and then when it's just x minus 1 squared and the square root of that, then those two cancel, and then minus 1 plus 1 is x. Same thing over here. I cannot cancel the square root of x and this 2 because both of these are still in this parentheses. So the first thing you would cancel is plus 1 minus 1 is 0. Then the square root and the square cancel, leaving you x minus 2 plus 2, which is x. All right, let's give these a shot now. So we want to check to see if these are inverses. So we're going to do f of g of x and g of f of x. So I'm going to start with f of g of x here. And so I get 2. And then I'm going to place this 1/2 x minus 5 in the place of the x here, squared plus 5. So notice that my f function, which is 2x squared plus 5, has not changed. It is 2. This is my new x squared plus 5. So I've taken the g of x function and I've placed it inside of the f of x function, in the place of the x. Now I can start to simplify this. So we've got a square root raised to the second power. And so that square root and that square cancel since it is the only thing inside the parentheses here. And so we get 2 times 1/2 x minus 5 plus our 5. Now, at this point, in order to get rid of the parentheses, I need to distribute. And so 2 times 1/2 x is 1x. And 2 times a negative 5 is a negative 10 plus 5. So in this case, I got x minus 5. I can go ahead and stop right there. I don't have to do the g of f of x because this is not x. In order for it to be inverses, they both have to be x. So these are not inverses. All right, here comes our last one. We want to do f of g of x for this one as well. And so my f is 3, and then I'm going to place this x minus 2 over 3 squared plus 2. So 3x squared plus 2. I have not changed the f function. All I've done is take this and place it in the place of the x. Now we've got a square root and a square, and that's the only thing in there. So the square root and the square cancel. And so we get 3 times x minus 2 over 3 plus 2. The square root and the square canceled. 3 and 3 are going to cancel now because this is in the denominator, this is in the numerator. And we get x minus 2 plus 2. Negative 2 plus 2 is 0, so that goes away, and we do have an x here. So this is quite possibly an inverse, so now I need to check my g of f of x. So I'm going to go ahead and have the square root, and in the place of this x right here, I'm going to put my f of x function. So I get 3x squared plus 2 minus 2 all over 3. So now I'm ready to start simplifying. Plus 2 minus 2 is 0, so I can cancel those out. And so I get the square root of 3x squared over 3. Then the 3's cancel out because 3 divided by 3 is 1. And so I get the square root of x squared. And again, that cancels and we get x. So g of f of x is x. Both of these turned out to be x, so they are inverses of each other. On the test, you will have to do one of the compositions to prove their inverses, and then you'll have several other compositions to do.